Thank you. My name is Hongru Chen. I'm going to talk about parallel high-fidelity trajectory optimization, and I will talk about it through an application of the CubeSat deployment in Earth Moon Halo orbit. And I want to acknowledge my other contributors, Mickaël Gastineau, Daniel Hestroffer, and Vishnu Viswanathan, and we are from Paris Observatory. And this work is sponsored by ESAP, laboratory of PSL, and the work is dedicated to a CubeSat project called Birdie. I will quickly review the difference between Earth CubeSats, interplanetary CubeSats, and interplanetary spacecraft. For Earth CubeSats, generally there's no need for orbit change or the propulsion system. But for CubeSats, we need to do some orbit change. And also in some cases, I know that you need to deploy the CubeSats away from the major spacecraft in order to secure the major mission. And also in some situations of cooperative operations, such as in the satellite ranging or in the interferometric measurements, we need to deploy the multiple elements into the space. So the CubeSats have to rely on their propulsion systems on board to get separated. And unlike interplanetary spacecraft who has relatively loose margin for propulsion, the propulsion capacity of CubeSats are greatly restrained by its limited space and mass budget. And so propellant budget is very critical to interplanetary CubeSats. Second, concerning the propulsion system, electric propulsion systems are getting popular because it's high specific impulsive. Which means for a certain amount of mass, the CubeSat can enjoy a high beta V budget. The drawback is that it's the low thrust, which may not be applicable for some trajectory needed for quick response. In addition, gravity of celestial bodies exerts influence on interplanetary trajectories. Whether the influence is positive or not depends on the Julian date. So we think the low thrust trajectories should be validated in the high-fidelity model. So we developed our our optimization tool for high-fidelity model. Like many other high-fidelity trajectory optimizers, our propagation considers continuous thrust instead of impulsive delta V, which is less accurate. And we also consider the mass loss of propellant loss. And of course, we take into account the ephemeris and gravity of celestial bodies. And we have included the solar radiation pressure. We should include, but we haven't yet included the higher order gravitational terms. So the objective of the observation is to minimize the propellant cost. And the optimization algorithm employs the idea of multiple shooting. So where we divide the whole trajectory into segments, and we set the initial condition of each segment's variables, and the optimizer tune the variables to cancel the difference at the continued connecting point. And the segments are considered uncoupled, so our propagator propagates both the trajectory state and also the first order partial derivative, which are used for guiding the optimization. And the Jacobi matrix is very sparse, so it's advantages for optimization. And this is a parallel algorithm, so it can be implemented in a parallel computing environment. So I will implement direct optimization using the Snap optimizer, which you can download online. We optimize the initial state of each segment and also the thrust vector to minimize propellant cost, and the solutions are subject to the initial condition and final condition, which are fixed to the halo orbit, and also the thrust magnitude shouldn't exceed the maximum the thrust can provide. And we implement the parallel propagation with using MATLAB Part 4. The propagator propagate both of the orbit states and then derivatives, and we derive the objective and constraint gradients. This information can guide the optimization, and in this way we improve both robustness, speed, and accuracy. And for the ephemeris software, I found that the JPL SPICE tool cannot be implemented in a parallel computing environment, and they admitted that. And luckily, we have a CalCAF, which is developed by Paris Observatoire. It's compatible with parallel computing environments, and it's available in C, Fortran, MATLAB, Python. So if you are interested in optimizing trajectories in parallel, you should consider CalCAF. So this tool is intended for the CubeSat project. Birdie is planned to perform radio science around a small body, but we haven't settled the flight scenario for this project, so I haven't applied my tool to this project, so I can't show you any results. So instead, I will show you the results of applying this tool to another mission. That's to apply multiple CubeSats into the Earth-Moon L2 halo orbit. And the mission is to provide positioning service for the assets on the far side of the Moon. And I'm not talking about mission or system design in this talk. And for this page, I will just say that with the required components, in this case, the basic payload is the communication system and also the clock. And the mass of the CubeSats without propulsion system is 4.2 kilogram. Next, and I have done some mission design and also have designed the trajectory, and some results have been published and presented in other conference, and I will present the mission design in the coming course part. Just quickly to mention that for better coverage of the far side of the Moon and better positioning accuracy, it's required to deploy 4 CubeSats evenly throughout the halo orbit. So at the beginning, the 4 CubeSats are released at the one point of the halo orbit, and by using phasing trajectories I designed in the simplified model, the three-body circularly restricted three-body problem. When they arrive at the halo orbit again, they are separated from each other evenly. So the result is showing the table. So I want to mention the third CubeSat, which needs to gain the delta V of 100 meters per second in only 48 days. We are afraid that this quick response cannot be fulfilled by low thrust propulsion system. And just want to check the existence of a solution with respect to the thrust magnitude. So the x-axis indicate the thrust acceleration. So when the thrust acceleration, this optimization is done in the simplified circularly restricted three-body model. It's just for a quick check. The thrust acceleration is considered constant for each round of optimization. So when the thrust acceleration is low and the delta V is maintained at low level, when the acceleration goes low, we need the high delta V, and when it's lower than some points, we cannot find a solution. For better interpretation, let's say the CubeSat is of a mass of 5.3 kilogram. The thrust magnitude should be greater than 0.4 millinewton. Otherwise, there is no solution. So I did some investigation and found some types of propulsion systems that meet the delta V requirements I showed before for the thrust that they have. So for the PHITO bat electro spray thruster comes with relatively high high thrust. 0.7 millinewton is higher than other electric thrusters we can find. The third line, the CubeSat one, occupies more space and mass, but its delta V budget is smaller than the electric one. And the first two chemical propulsion systems outperform in terms of all indices, but the chemical thrusters are considered less reliable or stable than co-gas and electric systems. In case we have to use electric systems for the CubeSats, I optimized the low thrust trajectories on different, starting on different Julian dates. I used the CubeSat mass I just showed, and also the CubeSat specifications. And blue points show the propellant cost. They are measured by the scale on the left. The black points are the corresponding delta V cost measured by the scale on the right. And the red points on the top are the indicated dates we can't find a solution. Although I may need further some more work, some more effort to validate whether it's the fault of the optimizer that cannot find a solution, or it's simply that there is no solution on those dates. Let me just assume that there's no solution on those dates, and the conclusions are the feasibility varies greatly with the mission date. So analysis in a simplified model is certainly not sufficient. And if we get to choose a mission date, we see here the biggest difference between delta V is 25 meters per second. So if we can choose a date, we can have a saving of that amount. But the sad news is that for most CubeSat missions, we don't get to choose the date because it's a secondary payload. You have to, the mission date generally comply with the major mission. And in this case, I would say chemical and co-gas systems are more suitable because low thrust trajectories are not always available. This is a trajectory example. The red line is the low thrust trajectories in the full-ephemeris model, and it's compared with the black line, the baseline trajectory that we designed in the three-body, circular restricted three-body problem. So we see the low thrust trajectories deviate from the baseline trajectories quite a lot, especially on the side of the halo orbit. So to sum up, we are developing a parallel high-fidelity trajectory optimization tool for the design and analysis of the interplanetary CubeSat trajectories, and the tool takes into account the specifications of propulsion systems, and the algorithm is run in parallel environments, and our propagator propagates both trajectory state and derivatives for facilitate the optimization. And we see that for low source trajectory, the trajectory of feasibility and database cost greatly depends on the Julian date. So we suggest that for the design and analysis of low source trajectories, we better always use full-ephemeris model to validate. That's it. Thank you.
It seems like a tool like this could be very useful, but it could also result in some very complicated thrusting profiles to be recommended for emission, which could result in quite high costs of operation. Could you add a module to the tool that also calculates the operations cost based on some parametric model, so you could also optimize it for lower operations costs too?
I'm not sure. I mean, it can be applied to.
The more different kinds of thrusting you do, the higher the operations costs.
Yeah. Yes, it can be analyzed, but the original purpose is to serve for low source CubeSat trajectories. But of course, it's a trajectory optimization tool that can be applied to other scenarios as well.
Any other questions?
Thank you. Perhaps this is a common question for simulations, but how do you validate your simulation results? Is somehow correct? Is there any way to compare some other results to say your simulation tool is the right one, correct one?
Oh yes, right. It's correct. Actually, we have other colleagues developing propagators, high-fidelity simulators. We can do cross-check, and so far the result is just confirmed. With my code.
So you compare your result with different models, different codes?
I think it's not necessary to be different models, just maybe a code developed by someone else. Maybe you can change the ephemeris files, and there may be some errors from different ephemeris files.
Any other questions? Well, I have a question. So you have quite a lot of data.
Yeah. Yes.
Sorry. There were quite a few days when you couldn't do transfers as much as you could. Did you look at sort of times within days? So are there sort of nice big chunks of time?
Yes. It's difficult. I computed for a period of 2 years, and then you have to. It's difficult to decide whether I have to pick every 1 day or every 10 days. I picked every 10 days. I don't know if solution exists in a very timed slot, but it's not very practical anyway. So you should need a window like 20 days or so. That's too
No, I
small.
was just checking to see how long those windows actually are.
Yes, computation.
Okay, so there are a few questions. Is that all speaker?